In this video, we are going to be discussing the solubility product constant. Before that, I'd like to remind you, feel free to comment or reach out to me in case you have any questions or need any clarifications on any topics. Also, I noticed that we have 500 subscribers in this channel, which is surprising. If 500 people showed up at my house right now, that would be a lot of people. And I'm so grateful for every one of you to have listened to my videos and who've found it really helpful. The reason I post these videos is for you. So what we're going to do is solubility product constant. For some reason in your textbooks, it just makes it a lot more confusing and it's a lot more complicated, and I just didn't like it. So what we're going to do is we're going to talk about 3 specific examples. Okay, we're going to take the example of barium sulfate, and then we're going to talk about zirconium phosphate, and then we're going to talk about a general equation to finish the whole concept up. But before that, for us to understand the solubility product constant, we are going to take an example of a saturated solution of a sparingly soluble salt. A sparingly soluble salt, as the name suggests, is a salt which does not want to dissolve in water. Okay, so basically we talk about the equilibrium between the undissolved salt and the ions of the salt. That's how we're going to understand this concept. Okay, so a saturated solution, we know the meaning of it, but if you don't, it's basically the one where no more solute can get into the solvent, right? So it can there's undissolved substance at the bottom, and for a sparingly soluble salt, it's very easy to get to that point. So let's start with the first example, which is going to be barium sulfate. Let me, oh, where is the other window? Okay, yes. So barium sulfate. So in a saturated solution with water, barium sulfate, you have barium ions, Ba2 plus and SO4 2 minus ions. Okay, these are formed. So the first step we're going to do, as always, is try to find the equilibrium constant, right? So, oh no. Okay. So K is equal to the concentration of the barium ion, SO4 2 minus, divided by the concentration of BaSO4. Now, as you know, this is the chapter equilibrium, so we're always looking for the constant value. And in this case, it's going to be I'm going to use the blue pen. It's going to be the barium sulfate, the concentration of this, because it is a sparingly soluble salt, so we're going to assume it's not changing much, so we will push this to the numerator, and that is going to give us this particular equation, right? So you have barium sulfate and then the concentration of barium ions and SO4 2 minus ions. So this K into the concentration of barium sulfate is the KSP. So KSP is basically the there it is the solubility product constant or the solubility product itself. So in the above, if for barium sulfate, the value of KSP is going to be equal to 1 at 298 Kelvin is going to be equal to 1.1 into 10 to the power minus 10. Now I want you to pause and think, why did we mention the temperature? If you said the solubility is affected by temperature, you would be right. So at a specific temperature, so 298 Kelvin, we're going to have that specific temperature. The value of KSP for barium sulfate is 1.1 into 10 to the power minus 10. Okay, so this is what it says in the first one paragraph of your textbook. Okay, they're taking the example of barium sulfate. Now, the next step is where I got a little bit confused, but I hope to explain it to you, and I hope it all makes sense. So the next thing we talk about in this topic for barium sulfate in relation to the solubility product constant and all the things is the molar solubility. So the molar solubility, which they do not define it in your textbooks, for some reason they had that just one sentence and they made it complicated. I don't understand why. But so basically, the number of moles of solute which is getting dissolved in 1 liter of saturated solution is the molar solubility. So it also helps us define the concentration of the ions in the saturated solution. So basically, in our solution, you have one barium sulfate, one molecule of barium sulfate gives us one ion of Ba2 plus and one ion of SO4 2 minus. So we are going to assume that S is the molar solubility, right? And you get 1.1 is equal to um, S into S, which is S is denotes one ion of barium 2 plus and one ion of SO4 2 minus. Okay, so we're just saying that this is equal to the concentration we're assuming is the value S, which is equal to the molar solubility. Now, then you get S square equals to is equal to 1.1 into 10 to the power minus 10, and then we're just solving for the value of S. So you get S equals to root over that, and then you get 1.05 into 10 to the power minus 5 moles per liter, because it's the molar solubility, and molar solubility is going to be is basically concentration in moles per liter. And notice KSP does not have a unit, but the molar solubility does. Okay, so what we just did was use the value, we substituted S and then we calculated the solubility, the molar solubility of barium sulfate. So we are able to figure out the solubility using the value of KSP. That is what we're trying to do over here. So just getting the value of the solubility product constant or the solubility product is not enough. We're able to calculate the value of S, which is the solubility of that particular salt. Now, this is going to be like the best case scenario where you have one ion each, but that's not how life works, right? There are cases where you might have more than one anion or more than one cation being formed. So that is where the example of zirconium phosphate comes in. So zirconium phosphate has the formula Zr3PO4. Okay, so this is in equilibrium to give us 3 zirconium 4 plus ions and 4 phosphate ions. And so obviously we know that the math is going to get complicated because of that. So first of all, we have the equilibrium, the KSP, sorry, the solubility product constant. KSP is going to be equal to the concentration of zirconium to the power 3. So we have to consider it's based on our equilibrium equation, right? We've learned this from the beginning of this chapter. And phosphate ions to the power 4. Okay, we're considering these numbers, and we are making sure that we are counting those numbers. Okay, so the next thing, obviously we want to try and calculate the solubility of the particular salt. So we have that, so Zr4 plus. Okay, now in the previous example when we took barium sulfate, because you just had one ion, we didn't have to consider the stoichiometry, we didn't have to consider any of those things. So we just throw S into S. But in this case, because you have a difference in the number of anions and cations being formed, we have to consider the stoichiometry of the reaction. So this 3 over here, you'll have 3s because 3 ions of zirconium is formed. So we have to see 3s. And then PO43 minus the phosphate, you have 4 ions being formed. So you have 4s. Now you can say, okay, why are we just considering it twice? In this case, we considered it for the equilibrium constant equation. They're two very different things. And then in this case, we're considering the stoichiometry. So do not get confused. I know it might feel like a lot, but basically we have to consider in both the cases because we have to consider the equilibrium constant equation as well as the stoichiometry. And believe me, I was trying to figure this out myself. So what we'll do is we will substitute this directly into our equation. So you get 3s to the power 3 into 4s to the power 4, because Zr4 plus the concentration is equal to 3s, and then phosphate is 4s. And then when you, I like showing you the math. So you get 27 s to the power 3, 256 s to the power 4. And then you end up with this particular value, which is KSP equals to 6912 s to the power 7. Okay, now we're still, the reason we got into all of this is to figure out the value of S. We're trying to figure out the solubility. So S to the power 7 will be equal to KSP divided by 6912, right? We just move things around, and then you end up with this particular equation for zirconium, where S is equal to KSP into KSP divided by 6912 to the power 1 by 7. If this feels like a lot, it probably is, because it's a lot of equations that I just threw your way. But basically what we did was we just took the value, the equation for KSP, and then we substituted the values of the concentration of ions with the molar solubility values, or molar solubility. So that is 3s and 4s respectively, and then we just solved for S. Now you're probably wondering, okay, fine, I learned this. Is there an easier way for us to remember that? It might be easy, it might be hard, but when you have a general example like this, where you have mxp plus nyq minus, I know in your textbooks it had x twice, and I did not like that, so I changed it. And so this particular salt is giving us xmp plus cation plus ynq minus anion. Now, the same thing as what we did for zirconium, right, where we had 3s, right? The same thing we're doing over here. So we'll have x number of ions into s, y minus y number of y into s. Okay, so KSP equals to the concentration of these guys to the power of x and y respectively. And then you're solving for we're just simplifying the equation, and then we are solving for S. So S equals to KSP divided by x into to the power x, y to the power y into 1 divided by x plus y. What we can do is let's go back to the example of zirconium phosphate. Okay, so zirconium phosphate, I'm going to write that out over here. So zirconium phosphate, yeah, okay. So X for zirconium phosphate was equal to 3, right? Because we had 3 ions forming. Okay, sorry, I'm just going to write that equation out as, actually, you know what? We're just going to copy paste the equation here. Why did that not work? Why? Interesting. uh, okay, fine. Okay, so it worked. So you have this, right? So here we have the value of x is equal to 3. And then you have the value of y equals to what? 4. So according to this equation, we should just be able to get that relationship. So S would be equal to KSP divided by x, which is 3 to the power 3 into y, which is 4 to the power 4 whole to the power 1 by 3 plus 4, which is 1 by 7, right? So we have 1 by 7 KSP, which is Three threes are, oh my goodness. I'm gonna pull up a calculator because, math. So 3 into 3 into 3, which 27, which this I know, okay? Please don't judge. Oh, whoops. Okay, we're gonna continue up here. So you have KSP equals to 27 into 4 to the power 4, which I'm pretty sure we did that the last time as well. 256. You have 256, and 256 into 27 is equal to, you will get to the exact same number, 6912. So KSP divided by 6912 to the power of 1 by 7, which is the same number we got over here as well. So this is another way for us to be able to calculate without having to go through all the steps to be able to calculate the solubility of that particular salt. Now, the last one that we're going to talk about, in your textbook, they did speak about the relationship between KSP and QSP. So KSP is the solubility product at equilibrium. QSP is going to be the solubility product quotient, so it doesn't really have to be in the equilibrium state. So it can be at any point in time. So when at equilibrium conditions, both KSP is going to be equal to QSP. But when the concentration is not in equilibrium, then obviously it will be able to give us the information of if if there's precipitation going to happen or dissolution. Which, by the way, I will say we will be talking about a little bit more in the next video when we talk about common ion effect. Now, the last thing you have in your textbooks for this topic is the solubility product constant of various salts. There was one thing I just wanted to mention. The solubility product constant gives us a relationship between the, it identifies the degree to which the salt gets separated or dissociates in water. So the more higher the value of the KSP, the higher is the solubility. So for example, sodium chloride, which we know is extremely soluble in water, it's not a sparingly soluble salt, but it's extremely soluble. It has a very high value of KSP compared to any of these. I think it's like 36 based on what I was able to find. So that's basically why we're using the solubility product constant. It's helping us identify if a particular salt is able to dissolve and to what extent it's able to dissolve, what is the can it precipitate out, and all of these are actually very useful when, I don't know if this is a lab activity that's still done, but when I think it was when I was in college, but we were able to be able to figure out the ions based on the precipitation, and that's all related to these concepts. So that is basically solubility product constant. So we discussed 3 different examples. We talked about the barium sulfate, zirconium phosphate, and then we talked about the general example. And the general example basically gives us a way to identify the solubility, the molar solubility of a particular salt. I hope all of that made sense. Again, feel free to reach out in case you need any other help with any other videos or help with any other concepts that I may not have posted yet. With that, we're done with the solubility product constant. In the next video, which is going to be the last conceptual video for equilibrium, we're going to be talking about common ion effect.